Hello, everyone. Welcome to part one of this two-part conference on energy and climate change, which, as the title indicates, will be about science's lessons on physical reality and green growth. Why two parts on the same topic, energy and climate change? I pretty much gave the answer in the flyer, which you all read very cautiously when you signed up for the webinars. But just in a nutshell, basically, I'll say that the arbitration community has been talking quite a bit about climate change over the last few years. Some notable initiatives have been taken, notably to reduce the carbon footprint of most participants in the arbitral process. I'm thinking of the remarkable Green Pledge that was started a few years ago and that's been adopted by many law firms and arbitrators. However, I also suppose that if we want to play a broader part in the broader scheme of things to help mitigate the effects of climate change, I think we must first understand, like all actors of, like all economic actors, we must first understand the challenges posed by climate change, which supposes basically that we understand the basic concepts of physical reality and the related science. Only once we've understood those basic concepts can we participate or devise plans that will help mitigate the effects of climate change, be it on the political front, on the economic front, or in the legal arena, including international law and arbitration. When you basically signed up for this webinar, you may have noticed that in the phrase green growth, the word green was between quotation marks. This will become apparent a bit later why we've chosen to do this in the webinar. But I wanted this phrase to be discussed and analyzed because the phrase green growth is a phrase we hear almost ad nauseum by governments, businesses, the media, economists, lawyers, basically everybody. So we'll need to give some thought to that particular phrase. When you signed up for this webinar, you may also have noticed a couple of items that are quite unusual for the Paris Arbitration Week. And in fact, I believe they're even possibly unique. First of all, among the 75 odd events at the Paris Arbitration Week, this is, I believe, the only event at which there will be no panel, but only one speaker. Second of all, I also believe this is the only event in which all of the talking for the next hour and a half will be done by someone who's not a member of the arbitration community in any way, shape, or form, as far as I can remember. A last couple of words before we start formally this webinar, and before I introduce our speaker. I'd like to explain very briefly why, for me, inviting our speaker was very important. And to explain that, I'll just talk briefly about what I know best, the subject on which I'm the most qualified in the world, which is myself. And recently, well, actually, after I became a father, some of the most enjoyable time for me for about 10 years as a parent was to go to a fantastic fish restaurant in Galicia, which is in the northwestern corner of Spain. I went there countless times as a kid, and I went there repeatedly with my parents, my wife, and my two children. And not long ago, I thought that 20 years from now, maybe this restaurant, this really fantastic restaurant, will be out of business because of rising sea levels, or possibly because of the depletion of oceanic life. But I'd like to be a bit more optimistic. And I think 20 years from now, I'll be eating lunch at this fantastic restaurant with my wife, my two children, and possibly my grandchildren. And when that day comes, and hopefully it will come, I'd like to brag about my contribution, however minor it might be, to our efforts to mitigate the effort of climate change. And if things go south, I also would like to be able to look in the eyes of my kids and possibly my grandkids and say, I've done whatever I could. One thing is to be remembered: no matter what we do, this planet will survive. I think it will do just fine. However, we're not so sure right now what will happen to us in the next few decades and our offspring. And I think inviting our speaker, Mr. Jean-Marc Jancovici, to speak about the physical reality and the related science is a way for us to understand that we should not be shooting in the dark when we're dealing with climate change, and for us to provide adequate solutions in our practice when we resolve disputes relating to climate change. And by us, I mean all of the Arbitration Council, the in-house lawyers, the professors and the students that signed up for the seminar and are presently taking part in the seminar. So before we formally open this webinar, I'll just say a few words about our guest speaker, Jean-Marc Jancovici. Jean-Marc Jancovici is very well known in France because he's possibly the foremost figure on energy transition and climate change issues in France. Jean-Marc Jancovici is an engineer who's authored several books and numerous articles on energy and climate change. He is a member of France's Haut Conseil pour le Climat, which is the body that advises the Prime Minister on climate issues. He's also a founding partner of Carbone 4 and the president of the Shift project, that are respectively the leading consultancy and a consultancy in energy transition and climate change adaptation in France. Jean-Marc Jancovici is also, among many other things, a professor at l'École des Mines Paris Tech. And by the way, I do recommend that for those who speak French, you have a look. It's on the internet, easy to find, at his 2019 or 2020, I don't remember, class on energy and climate change at l'École des Mines. It's 20 hours, and it doesn't take a math genius to understand the issues he's talking about. And pretty much anybody has 20 hours over a few months to devote to the subject. And I found personally this lecture to be extremely enlightening. And Mr. Jancovici has also been for many years one of the France's delegates at the various COP conferences. So I'll stop talking because this is the least important part. The really interesting part is going to start now. Jean-Marc Jancovici will have the floor for the next hour or hour and a half, depending on how long he needs. And then we'll have the remaining time for questions that you may ask in the chat, and we'll take as many questions as we can, bearing in mind that some of the questions may require detailed answers. So we'll do our best. Thank you very much for coming up. And now I'll give you the floor, Jean-Marc.
Thank you very much. I'm going to show you a number of pictures because, as any good consultant, I cannot do anything without slides. Or actually, I'm going to show you a subset of the slides that I use for my for the teaching that I give at Paris Tech. And now you should see my slide, correct?
I do.
Okay, fine.
And the participants will let us know if they don't.
Okay, so what I will try to explain right now, for those of you that are in a hurry, is that the short answer to the question that you have in this title is no. It is not going to be a piece of cake to go low carbon for real. And actually what you will see is that about everything you do in your daily life, including the job that you have, required so far that we have a high carbon civilization. The world that we live in is a remote descendant of climate stability. As you may know, a long time ago, the Earth was very much colder than it is today. We were living in an ice age with mammoths and so on. And for the last 10,000 years, the climate has been warm and stable. This has enabled our species to settle down, to begin settlements that are necessary, by the way, to have private property and therefore laws. Before that, I don't think that there were many lawyers when we were still hunting for food. So the world that we live in, with agriculture, cities, and all the organization that we have around cities, is actually, or actually inherits from one main component, which is that the climate has remained stable for the last 10,000 years before we began to change that a little bit. What you can see on this graph is the average planetary temperature. So it's the average, what is called the near ground air temperature, average over the surface and over time. And you can see that this average has remained close to the pre-industrial temperature, the temperature that we had on Earth before we began to pour greenhouse gases into the atmosphere, which is the 0 on the scale. And you can see that for the last 10,000 years, this is the beginning of the Roman era. So this is 10,000 years before the beginning of the Roman era. And you can see that for the last 10,000 years, the climate has been very stable with an average temperature of the Earth, which is close to what it is today. Okay. This has allowed, as I said, settlements. Before that, we were hunters and gatherers. We couldn't settle down because the climate was changing all the time. It enabled agriculture and it enabled cities. So it enabled all the modern, I would say, organization of humanity, including laws and people that are required to enforce the law or I would say, work for those that have disputes. We began to change that about a century and a half ago through pouring greenhouse gases into the atmosphere. Here you have a graph that shows human emissions of greenhouse gases. A greenhouse gas has a very simple definition in physics. It is a gas that has the ability to absorb infrared radiation emitted by the Earth. As you may know, all bodies that are heated enough emit infrared. Your own body, for example, emits infrared. When you're dead, it emits less. So when you are around 40 degrees Celsius, you emit infrared. The average temperature of the Earth is around 15 degrees Celsius, so it's close to 40 degrees Celsius. And the Earth's surface also emits infrared. And it happens that this infrared radiation cannot freely go to the space. Of course, this radiation is emitted by the Earth because the Earth is heated by the sun. And this radiation cannot go freely to outer space because it is absorbed by greenhouse gases that are present in the atmosphere. So the more greenhouse gases you have in the atmosphere, the more the energy that tries to leave the surface cannot do so. And so the hotter or the warmer it is close to the surface. So here you see again greenhouse gases that are emitted in the air by human activities. The main greenhouse gas emitted by our activities is carbon dioxide, CO2, but you can see that we also emit methane and we also emit other gases, nitrous oxide, halocarbons, etc. Well, I will elaborate just a little on these gases later on. What I just want to say on this graph is that what you can see is that since the second industrial revolution, these gases have risen, or the emissions of these gases have risen, whatever we believe could have stopped it. For example, we have developed electricity. In 1945, the electricity production in the world was close to what it is in France today. So the usage of electricity has tremendously increased, and it has not decreased emissions. Actually, emissions have increased. We have more trains today than we had half a century or a century ago. You often hear that when you put people into trains, it allows to decrease emissions because trains emit less than cars. Where we have more and more trains, it doesn't prevent emissions to rise. You also hear that becoming digital is something that enables the activities to become dematerialized. And so logically, it should decrease the pressure on physical flows. But as you can see here, we have more and more computers since the 1970s. We have more and more computers, and obviously it has not triggered a decrease of the emissions. People work more and more in offices. We also believe that when you are in an office, you know, you come out from the office in the evening, late in the evening when you do your job, and still you have the trousers that are clean, your shirt are clean, etc. And so you believe that we work in a dematerialized environment because you don't have soot everywhere and you don't have grease on your hands. Well, obviously, the fact that more and more people work in offices is not enough to decrease greenhouse gases emissions, all the opposite. And again, becoming digital also is not something which is efficient. Something which is efficient is an economic crisis, as you can see here. Something which is a little efficient is a war, as you can see here. Something which is a little efficient is an oil shock, as you can see here. This is a spike regarding deforestation. It's not something which is relevant for what I'm saying. But so far, all technical progresses that we have experienced, all of them have never prevented the greenhouse gases emissions to rise, never. It happens that the main greenhouse gas that we put into the air, carbon dioxide, has a very, I don't know if I should say, naughty property. It is a stable molecule. As you know, carbon dioxide is an oxide. Carbon dioxide, obviously, is an oxide. On Earth, oxides are stable molecules. That's basic chemistry. For example, there is an oxide that you use every day, otherwise you don't smell good, which is water. Water is an oxide of hydrogen. Well, water has been present on Earth under the form of water for 4 billion years. So obviously, it is a very stable molecule. Since we have oxygen into the air, all the iron that we have on Earth has been oxidized by that oxygen. And now all the iron ore that you can find on Earth for the last 300 million years has been iron oxide, and it's stable under that form, the form of an oxide. Carbon dioxide is also a very stable molecule, meaning that once in the air, it is eternal. There is no process to remove carbon dioxide as long as it is in the middle of the atmosphere. The only processes that lead to a removal of carbon dioxide from the air is when carbon dioxide comes back in contact with the surface, and then it can be removed by one of the two following processes. Either it is taken back by plants through photosynthesis, but that requires energy because photosynthesis requires a photon, the light, sunlight, so energy, which allows the plant to break down the carbon dioxide molecule in two. It keeps the carbon, builds sugar, and then delicious whatever you eat, and releases the oxygen into the air. The other process that allows carbon dioxide to be taken back from the atmosphere is dissolution into seawater, but that's kind of communicating compartments. It's just that if there is more room into the ocean than in the atmosphere, carbon dioxide goes from the atmosphere to the ocean. But if one day we find a way to remove CO2 from the atmosphere, there will be more room into the atmosphere, and part of the carbon dioxide, which is in the ocean, will pop up back into the air. Because these processes, these removal processes are slow processes, because they operate only when CO2 is in contact with the soil, and because, or the surface rather, and because it is eternal as long as it is in the air, carbon dioxide, there is no reversibility in climate change. That is something which is absolutely crucial, meaning that with the carbon dioxide that we have already emitted, we have created an additional stock of CO2 into the air. We have built up an additional stock. So the concentration of CO2 is higher than it was before we began to play with the steam machine and the internal combustion engine. The day we stop emissions, the surplus is not going to vanish overnight. Actually, 1 century after we stop emissions, that's what this graph says, 40% of the surplus, actually something between 30 and 60% of the surplus, will still be hovering over our heads, or rather the heads of our descendants. 1,000 years after we stop emissions, 20 to 30% of the surplus will still be in the air. And 10,000 years after we stop emissions, 10 to 25% of the surplus will still be over the heads of whoever will still be living then. So there is no reset button regarding the climate drift. Often we call climate change, we say climate change or global warming. I'm going to use the expression climate drift because it's exactly what is happening. You know, a drift is just like when you're sailing. It's a movement of the ocean that you just cannot do anything about it. You just have to cope with it because it is something so powerful, you just cannot fight against it. Well, it's exactly the same thing with the climate drift. We have put in motion something that we just cannot reverse. We just can't. There is absolutely no way we can now put the climate system back into its pre-industrial state. It is absolutely impossible, whatever we do. There are some consequences that can be stopped when the CO2 concentration stops growing into the air, but not all the consequences. Some of them will lag for more than 10,000 years now, whatever we do. So what is still in our hands is the ability to slow down the drift, to choose between a fast drift and a slow drift. That is still in our hands. But to prevent any drift, this is lost forever. And the issue is going to span over timescales which are way over what we are used to handle in our daily life. I would say the 1 or 2 generations is generally the longer thing that we can think about, not very often. And of course, this is going to span over time scales, which are much, much, much longer than any mandate of any elected person in the world. And we have adapted today the management of our modern societies to very small time scales, a couple of years, basically. The long-term strategy in any listed company is a couple of years. Time it takes to settle a dispute is also a couple of years, which is a little bit too long, by the way. And the mandate of somebody who is elected is a couple of years, well, so a couple of years. The average time that somebody stays in a given company, a couple of years. So we are used to managing, I would say, our daily lives with timescales that are a couple of years. And now we have to tackle a problem which is going to span over more than 10,000 years. As I've said before, that no technical progress has done anything to carbon dioxide emissions. It's the same for carbon dioxide concentration into the air that you can see here. So here you have a curve that gives you in parts per million. A part per million is 1 milliliter per cubic meter. Sorry for those of you that don't like the metric system, but I like it a lot. So even the US scientists use the metric system, so I hope you will excuse me. So parts per million, again, are milliliters per cubic meters, 1 per million. And you can see here, so the concentration of CO2 was a little bit below 320 parts per million in 1960. And it has risen slowly to over 410 right now. And you can see that nothing has stopped this rise. So no technical progress, but I can also say the same regarding the annual meetings of the countries, you know, what is now called COPs, which are meetings of the parties, meeting of countries that have ratified, I hope that to you guys, I don't have to explain what ratifying is, that have ratified the United Nations Framework Convention on Climate Change. As you can see, 1995, it is the year 1 of the convention. It's just been ratified by enough countries in order to enter into force. And it is the first meeting of the parties of the convention. Well, as you can see, that was before the convention. This is after the convention. You can doubt that the convention has changed anything. Kyoto is supposed to be a big success because it's the first year that developed countries took a commitment to decrease their emissions. You can see what happened later on. That's again, that's concentration, it's not emissions, but like as you can see, it didn't change anything regarding the trajectory of the concentration. Copenhagen is supposed to be a major failure. Okay. Paris is supposed to be a big success. Okay. Glasgow is not going to change anything on this curve. because actually what happens in COPs is not changing anything regarding the trajectory of the world. For those of you that are familiar with United Nations processes, as you know, decisions are taken by consensus. And when you take a decision by consensus, actually, all that you can do is acknowledge something that countries were already ready to do or already doing. That's basically what happens. So COPs, they are only useful to acknowledge what countries are already doing, which is not much. Something between not much and nothing. Here you have a curve which is showing the main marker of the climate drift, which is the average temperature near the surface. The zero on this graph is the reference temperature between 1850 and 1900. So it's the, I would say, the reference temperature, the planetary temperature of the second half of the 19th century. It was stable. Okay. You can see that in the 20th century, the average temperature of the Earth rises, and it has risen to 1 point something degrees of global warming so far. This 1 point something is enough to have triggered the death of 20% of the tropical corals on Earth. It is enough to have triggered the record temperatures that you have seen in Canada last summer, with the destruction, I would say, it could be a kind of divine justice. I mean, it was so brutal and so spectacular of a couple villages in Canada. It is enough for crops in some places to decrease by 40% from 1 year to another. It happened in Russia in 2010, happened in France 2018. It happened in the US for soy a couple of years ago. It was not 40%, it was a little below, but still. So with just 1 point something degrees, we can already witness consequences that are not marginal at all. Here you see what could happen to the average temperature depending on the future emission scenario. So this is often called a business as usual scenario, but I will explain at the end of this conference that it is not a business as usual scenario, because it is actually a no limit scenario. It is a scenario in which we have more and more oil, gas, and coal to burn until the end of the 21st century, with absolutely no adverse event halting the growth of our economies, which on a limited planet, on a finite planet, is something that I don't believe in a single second. Okay, so this will not happen because planetary boundaries will apply to humanity much before the end of the 21st century. So it is not a business as usual scenario. It is a fairy tale scenario. Okay. This is the Paris Agreement scenario. So it's a scenario in which we do agree to decrease emissions very, very fast. I will explain at what rhythm later on. And what you can see, the very striking thing on this graph is that you can see that between the no limit scenario and the Paris Agreement scenario, which is going on a very, very strong diet, I would say, starting tomorrow morning, actually there is no difference in what happens to the average temperature of the planet for the 20 to 30 years to come. I will take that parallel, which is worth what it's worth, which is that the climate drift is like a car for which the day you decide to push on the brake, the car is going to accelerate for the 20 years to come. Okay, that's the picture you should keep in mind. So not only we cannot stop the drift, but it's not going to make any difference for the 20 years to come, whether we act very strongly or whether we just say, okay, we don't care about the issue. It makes a huge difference for the end of the century. So we should act. But at the same moment that we act, we should also understand that we have to prepare for more adverse consequences than those that we have already witnessed. Okay, so we have to do two things in the same time, which is investing in what is called adaptation, but we will not adapt to everything. There are things for which we will only cry. or only suffer. And in the same time, we should also begin to decrease very strongly our emissions. And you will see later on that it is something which is very hard to do, because greenhouse gases come from a hard drug, which is called energy. So at the end of the century, again, scenarios make a huge difference. For the 20 years to come, they don't. Is it an issue to have the global temperature to increase by a couple degrees? Well, before elaborating on this graph, I'm going to take a very simple example, which is your own body. If you take your own body and you increase your internal temperature by 1 degree Celsius, or 1 degree Fahrenheit is even better. You feel a little sick, but if your client is paying enough, you won't even miss the office and you will go working. Okay. If your internal temperature increases by 5 degrees, you are not a little sick for 5 days, you are dead. So what I'm trying to explain with this simple example is that when you face a complex system, the consequences of a temperature increase are not proportional to the increase. They are not, it's not a linear response that you have between the temperature increase and the consequences. For your own body, the consequences of a 5 degree temperature increase is infinitely more damaging than the consequences, or are infinitely more damaging than the consequences of a 1 degree increase. It's going to be the same thing for the Earth, and I'm going to show it now with a simple example. These are the ecosystems that you can find in Northern America, I would say, before the Industrial Revolution, because right now it's already changing. As you can see, all Canada is covered with forests, and you have an arid part here in the middle of the western part of Northern America, but everywhere else you have, I would say, luxurious ecosystems with forests. This is Northern America 20,000 years ago. 20,000 years ago, the Earth was in the middle of an ice age, just as in the cartoon. As you can see, the geography of Northern America was very different from what it is today. First, at the time, there were no Canadians. Sorry, guys. All Canada was buried under ice. So was Scandinavia. So was Northern Siberia. All these places were covered with an ice cap that was roughly 3 kilometers thick. In order to build up this ice cap, you need to take water somewhere, just as when you have ice in the fridge, you need water. And this water has been taken from the ocean, but the ocean floor was in the same place. So the ocean was 120 meters lower than what it is today. As you can see, now you have islands here. At the time, you didn't have islands because the ocean was much lower. And human beings could cross the Bering Strait on foot, which is something that you can't do today, of course. What you can also see is that it was much drier and colder in most places that were not covered by ice. So when you look at the surface covered by forests, of course, they are much smaller, much smaller than the surfaces covered by forests today. You see, so I would say ecosystems of plenty were much smaller than what they are today. And the population at the time was much smaller because these ecosystems, these I would say meager ecosystems, could feed a population that was much lower than what the ecosystems could feed today, even with gatherers and hunters. Well, when the Earth went from, when Northern America went from the state on the left to the state on the right, it happened in the course of a global warming that took place on Earth, which is only plus 5 degrees in 5,000 to 10,000 years. So here you can see the result of a real experiment performed by a planet from 20,000 years ago to 10,000 years ago, which consists in warming the planet by 5 degrees. And you can see that it is a huge change in the environment. So this is for Northern America. You can see Europe, exactly the same kind of huge transformation. So now, when you see the type of change that happened for 5 degrees in 10,000 years, you can, of course, guess or deduct by yourself that if the climate warms by a couple degrees in a century and not in 5 to 10,000 years, and that you apply that change to a sedentary humanity of 7 to 8 billion people that cannot move very easily, the probable result is war and turmoil everywhere. And when I say everywhere, I mean everywhere, not only in some remote African country. I do mean everywhere. It is going to be such a huge disturbance that all you lawyers, either you work for the dictator or you are jobless. That's what is going to happen, because this is going to blow up democracies and stability everywhere. If I come back to the graph with which I've opened this small talk, so here you have the average temperature of the Earth for the last 10,000 years. So it's after, of course, getting out of the Ice Age. Getting out of the Ice Age is here. So you see, 20,000 years ago, there is roughly a 4-degree difference. I said 5, 4. Okay, that's the magnitude between the Ice Age that happened then and the beginning of the Holocene that you have here. This is the change that we have already triggered with our past emissions, and this is the change that could happen at the end of the 21st century with, I would say, a business as usual scenario, including the fact that the business as usual scenario will lead to a peak CO2 emissions somewhere in the coming decades, because we will have less and less oil. I will elaborate on that at the end of the presentation, and more problems of any kind that will prevent growth from happening. So even with this business as usual, which is some kind of bumpy scenario, we could have at the end of the 21st century a temperature rise which is of that magnitude, but happening in a glimpse of an eye compared to the time it took to warm the planet from the last ice age to, I would say, the beginning of the Holocene. You can see that it's, of course, something which is extremely brutal if it happens, and the consequences are going to be absolutely tremendous. And again, keep in mind that a 2-degree warming is not twice as bad as a 1-degree warming. Might be 1,000,000 times as bad, okay? Because it's a non-linear response. Now let's look at a couple consequences that could happen. This is a map that has been published in a paper a couple of years ago, I think it's 2018, which gives the number of days for a various number of places, the number of days in the year for which external conditions will be deadly if the average temperature rises by 4 degrees compared to today. So it's 5 degrees compared to pre-industrial times. Why conditions are deadly? Because the external temperature is over the temperature of your skin, roughly 35 degrees. And the rate of humidity of the air is 100%. So you cannot sweat to evacuate your internal heat. If you cannot evacuate your internal heat, either through sweating or through radiating heat to the ambient air, because the temperature of the air is over the temperature of your skin, you die. And you can see all the countries for which the color is over, I would say light red. For all these countries, the external conditions are deadly more than 1 day out of 2 all year round. Meaning, particularly, that you cannot perform agriculture, which requires usually to be outside, which means that people die. So, of course, people will not remain idle in the countries, gently waiting to die. This will trigger migrations, and you can see that the population at stake is roughly 2 billion people. Question: do you think that if 2 billion people feel uneasy where they are and want to move somewhere else, on a planet which is populated by 8 billion people, it's going to be a very calm story? The answer is obvious. Of course, no. This is going to trigger wars and turmoil. the climate drift is not only going to change the temperature, it's also going to change humidity, the water cycle. It's going to increase precipitations in some places, decrease them in some other places, increase the intensity, the intense precipitation events, as we have just witnessed on the eastern coast of the US recently with Ida, in Northern Europe recently also with the floodings that we had in Belgium and Germany, with intense monsoons that happen more and more in Asia. But these precipitations can increase in volume, in global volume, but be concentrated on small events with longer dry spells. All this is possible, resulting in drier soils. And if you have drier soils, the people that live in the western part of the US right now know it very well, it's a little issue for growing food. So here you have the evolution of the humidity of soils in the change for various scenarios. This is the Alice in Wonderland regarding emissions. So this is the no limit scenario. This is the Paris Agreement scenario. And this is the 2-degree scenario, roughly. And this is a 3-degree scenario, roughly also. What you can see is that in a number of places, for example, the southern part of Africa, for example, the Amazon basin, which is not very good news because that's where you have the largest forest in the world, soils are going to become drier, which means that both ecosystems and agriculture are going to suffer. Okay, that's what it means. Both ecosystems and agriculture are going to suffer. And this is particularly true for Europe, which is very bad news for me because that's where I live. And you can see that even with, you see a 2-degree scenario, it's already becoming significantly drier in some places in Europe. And it's going to be true actually in rough figures for all the surroundings of the Mediterranean basin. And here you have plenty of countries that are not self-sufficient in food with a growing population. So be prepared for more Arab Springs because it's just a matter of time. This is a graph taken for the last, a recent IPCC publication, which tries to qualify and quantify the consequences of a number of consequences. And the one that I would like to draw your attention on is this one. The color code on this graph is that when you are in yellow, it is local and manageable. And when it turns to purple, it is global and hardly manageable or unmanageable. And what you can see is that regarding food supply instabilities, triggering riots, of course, and from 2.5 degrees, it becomes widespread and hardly manageable. Okay. This is, of course, an element that is going to trigger, as I explained before, turmoil everywhere, because when people don't have to eat, generally, they are not very happy. This is something which illustrates an additional bad news, I would say, which is the fact that ecosystems, the ability of ecosystems to take CO2 back from the atmosphere is weakening over time. It is weakening over time because it has become drier and drier in a number of places where these ecosystems are located. And plants are just like you. If they don't drink, after some time, they don't like it at all. They don't perform well, and even they die. So the water stress has turned, after the year 2000, a very large number of ecosystems on Earth from a growing carbon sink to a weakening carbon sink. Actually, the color code on this graph is that if it is green, it means that year after year, the carbon sink is increasing because you have more CO2 into the air, the temperature can be a little milder, etc. And when it becomes red, it means that year after year, the carbon sink is weakening. So we still have a carbon sink, but it is weakening. So before the year 2000, on the top, you see it was increasing about everywhere. After the year 2000, or I'd say 1999, well, it is weakening in a number of places. It is still increasing in the Amazon basin, as you can see, in Southeast Asia and Africa. But it's unfortunately just a matter of time before in these places, because of climate change, it is also going to weaken. Extreme events have increased in intensity and will go on doing so. The reason why is very simple, or the basic reason why. As I've said, the climate drift, one of the consequences is that the average temperature near the ground is increasing. But it is increasing because the infrared emitted by the surface is trapped close to the surface. And therefore, if it is trapped close to the surface, it cannot go in the upper atmosphere and heat the upper part of the atmosphere from the ground. So one of the consequences of the climate drift is that the stratosphere is cooling down. So in the evolution that we have triggered, it is hotter close to the ground, colder in the stratosphere. So the temperature difference between the ground and the stratosphere is increasing, and that is increasing convective movements, which are the pump of all the extreme events, such as hurricanes, tornadoes, and even storms. So the models expect an increase of the intensity. It was the case in 2014, as you can see here. I've not put the latest graphs from the IPCC, but it is something that we have witnessed for the last 10 years. We have seen hurricanes growing in intensity faster than any hurricanes we have monitored in the past. We have seen hurricanes with extreme winds or extreme precipitations that are more intense than what we have monitored in the past, in recent years, etc., etc. So when you look at what is happening today, it is exactly what has been predicted 10 years ago. And the reason why, again, is very simple to understand. And this evolution is going to increase. This intensity, sorry, is going to increase. So all the extreme events are going to intensify in the future. It's obvious. Greenland has begun to melt. It has begun to melt because the temperature at the top of Greenland is already warm enough for part of the year for the ice to melt. So it's a melting process. Okay. It has, now that the melting has begun, you have plenty of positive feedbacks that ensure that this melting will continue. Nothing now can stop the Greenland ice cap to go on melting, nothing. Depending on the speed at which it will melt and a number of other characteristics, this will add 3 to 6 meters to the ocean level in the centuries to come. And there is a risk that the western part of the Antarctic, which is this part, you could wonder where is the west when you have a continent which is centered on the southern port, but that's the west. So the western part of the Antarctic, which is a house of cards of glaciers that each hold the next one. So you see, it's the idea of a house of cards. And all these house of cards or house of glaciers are lays on bedrock, which is below seawater. So all this is very unstable. And if you have an increased melting of the glaciers that are directly leading to the sea, it could destabilize the whole ice cap. And the whole ice cap could disintegrate in a matter of decades or centuries. This is potentially 6 meters extra for sea level rise. So in a couple centuries, if you read the last IPCC report, it is expressively written, black on white, and that's in that report, that a notion, that the sea level rise exceeding 16 meters cannot be ruled out for 2300. 2300. Of course, it is remote for us, but the finger on the trigger is today. The finger on the trigger is now. Because the ocean is taking back CO2 from the atmosphere, it is becoming more acid. This is going to make life more difficult. This is going to hinder the synthesis of lime for a number of organisms that you can find into the ocean. And so it's not going to be very good news for marine life. And again, the global ocean circulation, the one that creates the Northern Atlantic drift, going from the tropical belt to Europe, or to Greenland rather, is at risk of weakening or even collapsing. When the Earth increases in temperature, well, it's going to be good news for a number of microorganisms that are going to thrive. And so we should expect new diseases or new patterns for existing diseases, which is going to be very difficult to predict, of course, and very difficult to attribute ex post. Of course, it's not very likely that COVID has something to do with climate change, but climate change will trigger COVID-like pandemics and outbreaks, and it's going to be very difficult to say that this precise outbreak owes something to climate change, but it's going to happen. It's going to happen statistically. Carbon that was fixed in soils, or that has been fixed in soils for thousands or millions of years, could be put back into circulation, into the atmosphere, because of the first consequences of climate change. All this, of course, is going to trigger consequences on human societies. It is totally impossible, I mean it, totally impossible, to draw a precise inventory of all the risks that we run if the climate drift amounts to 1.58 degrees or 2.76 degrees or 3.12 degrees. Okay, this is fully impossible. No scientific community on Earth can draw the precise inventory of all the consequences that can happen because of the climate drift. So we have to, I would say, do what we can with the information that we have, which will be incomplete all the time. And because we cannot predict everything in advance, the only certainty that we have two certainties regarding climate change. The first one is that we'll have surprises. Okay, so you should prepare for surprises. You don't know which ones, or you don't know all the surprises that can happen, but we will have surprises because it is a first-time experiment. And when we perform a first-time experiment, we always have surprises. Actually, you people are paid to deal with unexpected consequences or unwanted consequences of what was supposed to happen. Okay, we were supposed to do things and it didn't happen that way. And so people have a dispute and there you are. So your profession exists precisely because sometimes we have surprises. And we have surprises in, I would say, regarding things that we have done for 1,000 years, business. So take a first-time experiment. It is obvious that we'll have surprises. So it is obvious that we'll have to manage real-time consequences that we couldn't foresee in advance. It is just, we just cannot avoid that. And the second thing that you should have in mind is that because of the inertia of the system, the day consequences become unbearable and unmanageable, the only certainty that we have then is that it will be worse afterwards because of the inertia of the system. So the day forests burn everywhere, prepare for forests to disappear later on because it's going to become worse. Because we just cannot stop climate change for decades and for some compartments for millennia. Okay. So it is a problem that we just can prevent. We cannot solve it. The idea that we will solve the consequences of climate change is just an illusion. It won't be true. Some people try to put a price on the consequences of climate change, an economic consequence. I would say, my conclusion is that this has no sense. Why doesn't it have any sense? Just because in classical economics, natural resources are free by convention. When I buy this glass, which actually I didn't buy, but Eliseo did it for me, the only thing that I don't pay is the glass itself. The atoms that constitute this glass are free. They have been designed by Mother Nature over the course of evolution for free. All that I have paid for this glass is human labor and rents that went from natural resources that are free to the glass that I pay. So money pays only human components. But if you don't have the matter to constitute that glass, so if I put clever engineers and clever lawyers in the middle of the vacuum, of the interstitial vacuum, I don't have any glasses. So I need the matter to build this glass, but the matter is free. It's exactly the same for all natural resources that we have on Earth. And it's of course the same for the climate system. So our climate system is free. You will never see in any corporate accounting so much for climate system. You will never see that. You will never see anything for the fact that we have 20% of oxygen into the air. But if you put people in an air without oxygen, they die and you don't have any GDP. So the economic production needs free natural resources. But because they are free by convention, how can you have a damage function on something which is free? If something is free, you just cannot, well, the cost of damaging it is zero. So harming the climate system, which is free by convention, is worth zero. It's very simple. So all the economists that try to build up damage functions for the climate system, actually the only thing that they can do is this. It's the only thing they can do, because there is absolutely no other way to put a price on something which is free. Okay. So some people say, okay, the cost of the ton of carbon, which I would say compensates or balances the damages, is $100. Some say 500. I just wanted to quote this paper where they say, these people, that it's between $10,000 and $600,000 per ton of carbon. You have to divide by 4 to get the ton of CO2 roughly, which means that these people coming from the university that I think so also Friedman, that is Chicago, they say that each time you emit 1 ton of CO2 into the air, the damage resulting from that ton could overall amount to $150,000, $150,000, which is generally 10 to 60 times the amount of GDP that you can have when emitting a ton of carbon. So basically what these people say is that it is a very bad idea, if we stick to economics, to emit CO2. We'd rather stop production instantly tomorrow morning than go on emitting CO2. Funny, no? Now, if we want to address correctly this issue and apply the Paris Agreement, you have this curve, which is a very important curve in the climate, I would say, in the climate debate. This axis gives you the overall amount of CO2 that we pour into the atmosphere from 1850 to 2100. Okay, so here it's the overall amount of CO2 that we put into the atmosphere. Here it's the temperature response of the climate system. And you can see that you have roughly a linear response of not the annual emissions, but the cumulated emissions of the temperature, to the cumulated emissions. Okay, so the temperature increase is responding linearly, globally, to the cumulated emissions. At the end of 2020, we are there. We have emitted on Earth about 2,300 billion tons of CO2. And so the global temperature has increased by 1 degree something. If we want to stick to 1.5 degree, we can do the reverse. We have to limit emissions to 3,000 billion tons of CO2, of which, of course, 2,300 have already been emitted. So basically, the carbon budget that remains to the end of the century, if we want to stick to 1.5 degrees, is 1/3 of the carbon that has already been emitted since the Industrial Revolution. As most of this carbon has been emitted since the Second World War, most of it, 80, 90% roughly, it basically means that a baby born today is entitled to a carbon budget over his lifetime, which is 1/10 of what his grandparents dead today have emitted during their lifetime. 1/10. That's what it means, the Paris Agreement. If we want to stick to 2 degrees, we can reason the same way. And basically, we can emit an extra big half of what has already been emitted until the end of the 21st century, with a population which is on average 3 times as numerous. So then the carbon budget of a baby born today is 1/6 of what his grandparents, dead today, have emitted during their life. If we want to achieve the 2-degree goal, which is the least ambitious of these two, it roughly means that we have to cut down, to slash emissions by two-thirds since 2050, which means that they have to decrease by roughly 5% each year, starting now, each year, until my kids are my age. That's basically what it means for all the years to come until my kids are my age, and then and thereafter. Emissions of a given year have to be 5% lower of the emissions of the previous year, and that's for each year. It happens that a 5% decrease is what happened during 2020 because of the COVID outbreak. So keep in mind that meeting the 2-degree objective means adding an extra COVID each year for the 30 years to come. That's what it means to achieve the 2-degree objective. Now, I believe you understand that it might be something very different from the green growth that we all believe in. And it's not totally sure that we are, I will end by this. If we want to decrease emissions, we have to know where they come from. So that may give you a little hint of where your future disputes will be. 20%, let's say, of greenhouse gases emissions come from coal power plants. Coal power plants alone, they account for more than 20% of the CO2 emissions, 20% of greenhouse gases all over, so including methane, nitrous oxide, etc. Half of these coal power plants are located in China. And you can keep in mind that all coal power plants in the world have to be dumped before 2050 if we want to be serious on climate change, all of them. 7% of the world emissions are, for a little part, oil and mostly gas power plants. Gas can be natural, but coal is natural also, as is oil. All those fuels are natural. Mother Nature designed them for us, produced them for us. So gas power plants also account for a significant chunk of the emissions. Producing electricity with coal or gas accounts for a quarter of the overall emissions of human activity. Okay, so there is obviously something regarding electricity. And of course, I suppose there will be questions on whether we will do it with only windmills and solar panels, because that's an interesting question. 7% of the world emissions are cement power plants. The cement industry is the first emitting industry in the world, if you exclude, of course, producing electricity with coal. So building cities emits plenty of CO2 because we have to manufacture cement to build buildings and infrastructure. 10% of the world emissions are the remaining industrial processes. That is only direct emissions. So for example, the electricity, which is used by chemical plants or steel mills is not included into this 10%. It's located there. Okay. So this is only the direct emissions. So you have blast furnaces here, you have petrochemicals, etc., paper plants. So you have the direct emissions because in all these plants you burn something to get heat. So all the industrial emissions, the direct industrial emissions, are about 17%. And of course, you could add the electricity production, which is used by this industrial production, and then it would go up to something between 25 and 30. 5% of direct emissions is heating buildings. Not all buildings are heated in the world, of course. 14% is transportation, among which you have 6% for cars, 4% for trucks, 2 for ships and planes before COVID. So you can see that, for example, cars in the world represent an issue for climate change, which is about the same size as cement plants. Transportation means altogether are a smaller issue than coal power plants. Boilers in buildings are about the same issue than cars overall in the world. Okay, blast furnaces emit about as much as trucks. I have not represented on this pie chart the emissions arising from our digital system. because they are located here for electricity, located here for manufacturing the device, located here for transporting spare parts, bits and device, etc. So this is only direct emissions of various sectors. 20% of our direct emissions come from agriculture. Agriculture emits through cattle. We have 1.5 billion cows on Earth that emit methane because of their four stomachs. You have because you have fermentation in the stomachs of the cows. You have rice paddies that emit methane because you have organic remnants that decompose away from the oxygen of the air. You have nitrous oxide coming from using fertilizers on the ground, etc. So 20%. 10 to 11% comes from deforestation, which is an upstream process of agriculture. Basically, most deforestation comes from the fact that we chop down trees in order to grow food, or to grow food of the animals, because most of the land today is used for animals and not for feeding directly human beings. And 7%, now the biomass of domestic animals outweighs by a factor 10, I think, the biomass of wild animals, and is about it weighs about the same than the biomass of humans. And here you have various other processes such as waste management, fluids that are used in cooling systems, etc., that leak a little, etc. About 2/3 of these emissions come from energy. So the first thing that I should ask is, okay, we have to decrease all these by 5% per year. Where do we start? Where do we start? What do we do? Okay. Where are the factors that drive the emissions? For example, deforestation and agricultural emissions have very little to do with coal, oil, and gas, and they have a lot to do with the size of the population and the share of meat in the diet. So if you care about deforestation and emissions coming from agriculture, your two concerns are the size of the population and what we eat, basically. Okay. So for each of the slice of the pie chart, of course, you have to understand the drivers, and it's not as simple as doing this and saying, okay, we just have to put renewables and the problem will be addressed. No, it's much complicated than that. And so you can see here that a big chunk, but not all of it, a big chunk comes from energy use, that is fossil fuel use. So energy, we're going to address energy. And of course, when you address something, as you may have had when you were a kid in school, sometimes, you know, the teacher asked, what is this and what is that? So I'm going to ask, what is energy? If you go at random in the street and ask people what is energy, chances are that you will get anything but the right answer. Something that you will get is it's a bill. Okay, it's something that I pay. It's of course always too expensive, so it's a bill. Unfortunately, it is a small bill. I'm going to take the National Train Company in France. You see, the National Train Company operates big machines like this one that use energy. And when I look at their balance sheet, I find people working for the company and energy. It happens that people working for the company represent 50% of the expenses, buying energy, and this company is the first electricity consumer in France. So it is the first industry. It uses 1.5% of all French electricity alone, 3% of the expenses. Now I ask a question. If I suppress 3% of the expenses in this part, what happens? Well, I get a strike, but I don't kill the company. If I suppress 3% of the expenses in this part, there is not a single train running, and I kill the company. What I want to say through this simple example is that the price you pay for energy is not the point. It is not the point. When you look at what energy weights in the expenses, it doesn't tell you the right story regarding the real importance of energy. Actually, when you look at what people pay for energy in the world, energy represents a couple % of the world GDP. And so all people think that, okay, we are going to devote to this topic a couple % of our available time. But this is about as sound as if I said, your brain is only 2% of your mass. So you should take care of your brain only 2% of the time. Or if I remove half of your brain, it's not a big issue. Okay, you will just lose 1% of your efficiency. No big deal. Of course, this reasoning is a wrong way to reason, because all your body depends on these 2%. And what I'm going to explain now is that all modern society depends on this 5%. So basically, we don't care whether it's 5%, 10%, 1%, or 50%. 100% of our modern society depends on that. Second wrong answer is that we should save energy. Well, actually, it's not what we have done so far. This is the energy consumption in the world for the last century and a half. Obviously, we haven't saved energy. We have used more and more, and I will explain in a couple of seconds why. Most of the energy that we use today is fossil fuels. It was already the case in 1980. Actually, from 1980 to 2020, the share of fossil fuels in the world energy supply has remained stable at 80%. Okay, 80% of what we use is fossil fuels. So, of course, modern renewables that you can see here on top, you see, it's the pink area. They grow, they remain marginal in the overall supply, but in the same time that renewables grew, coal grew, oil grew, gas grew. And actually, for the last 20 years, coal grew 7 times or 8 times faster than wind. So the reality today is that we are still living in a fossil world. We are talking a lot about renewables, but we are living in a fossil world. So it is not, Bill, we have not saved this so far. Some people regarding renewables say, okay, don't bother us with energy issues because we are going to be 100% renewable and the problems are going to be solved in green growth. Well, I've got good news for you. 100% renewable world is possible. It is definitely possible. I bet all my money on the fact that it is possible. Here is an example of renewable world. So a renewable world is possible. There is absolutely no question on that. Actually, the answer is so obvious that from the apparition of our species to 2 centuries ago, we have been living in a fully renewable world all the time. This is a fully renewable boat made of fully renewable wood, pushed by a fully renewable person, pushing on a fully renewable stick, navigating on a fully renewable river. The fully renewable wind is blowing through a fully renewable mill somewhere downstream. Here you have fully renewable terrestrial transportation, eating fully renewable grass. I mean, all this is fully renewable. There is absolutely no question on that. The good question is, will we be able to keep the industrial world that we have built up with only renewables? And now the answer to this question, my personal answer to this question, is not a single second. This is not going to happen a single second. And I'm going to end with a little rule of 3 explaining why. If it were possible, question, why is it that 2,000 years ago, with a proportion of genius on earth that was the same as today, Mozart was a genius. I mean, designing symphonies at the age of 5, nobody has done that since him. Nobody. Da Vinci was a genius. Newton was a genius. I mean, all these people were genius. Why is it so that with all these geniuses on earth, with the same proportion of geniuses, when we had only renewable energies, we saw no industrial civilization emerging, and we had to wait for that in order to see the Industrial Revolution emerging? Well, the answer is it's because of physics. It's not because we are evil when we use oil or coal. It's because of physics. It's because the concentration of this energy and the easiness with which we can extract energy from the environment is incredibly higher than what is possible with this kind of device to extract energy from the environment. It is physics. It is just physics. And so the good answer is not that energy is a gas bill. It is not that we have saved it. It is not that it is 100% renewable. Actually, the good answer is the answer D. And the answer D is this. This is energy. Energy is Iron Man. So you'll say, this guy needs a break, obviously. Let him breathe a little. No, this is Iron Man. Only it has not the form of Iron Man, the energy. It has this form. This is energy. But actually, this is Iron Man. Energy is the food of Iron Man, meaning it is the food of all these mechanical slaves, all these machines that work for us and have increased the power of our muscles by a factor 100, 10,000, a million, 10 million sometimes. You see, for example, this crane has the power of 10,000 pair of arms. So when the driver of the crane goes into the cabin, he instantly multiplies the power of his arms by 10,000. When the driver of the trucks climbs in the truck, he multiplies the power of his legs by 4,000. When you push the button on this washing machine, you multiply the power of your arms by 100. When you use this machine that, I don't know, whatever, knits, I don't know exactly what it does, designs clothes, you increase the power of your arms by 100,000, etc., etc., etc. So this is as powerful as a couple, 10,000 probably pairs of arms. This is as powerful as 1,000 pairs of legs. So even this small vacuum cleaner is powerful as 10 pairs of legs. Okay. If you look at all the machines that you have at home, it is just as if you had anything between 50 and 200 servants that were at your service all day round, all year round. Okay, that's what energy is. So energy is a hard drug because energy is power. Energy is what works for us. Energy is what enables us to accumulate more and more, which is something that we desire because it's embedded at the very root of our brains. That's what is energy, which is why it is so difficult to do without, because we have to fight against our own nature. That's what it is, because quitting a hard drug is something which is very, very, very difficult. But that's what we have to do. We have to quit a hard drug if we want to be effective against climate change. So this is energy. Energy is Iron Man. When you look at the power of all these artificial muscles with their own food, which is energy, well, you realize that all the fleet of machines on Earth at any time is multiplying the muscular power of humanity by 200. So I'm going to state that in other figures. It means that the economic production, the physical production on Earth, if machines, therefore energy, didn't exist, we would need to be 200 times more numerous in order to ensure the same production. So we should be 1,600 billion people on Earth to produce the same GDP. We already have a little problem with space. I think that with 1,600 billion people, chances are that we would have a slightly higher problem of space. In Europe, it's 600. In the US, it's 1,000. So the average US citizen is living, I say the average, even if I know that in US you don't have averages, but even though the average US citizen is living as if he had 1,000 slaves at his service all day round, all year round, in order to produce all that he is consuming. Another way to put that is that today, machines are working, we are not working, we are giving orders to machines. And so the production is ensured by something that needs energy, which explains why you have this graph, which is a logical consequence of what I've just explained. Here I have plotted for the years 1965 to 2020, the energy use of the world here, which is actually the size of the size of the active fleet of machines, the size of the active fleet of machines. And here you have the value of the economic production. And you can see that roughly you have something which looks like a straight line. And in 2020, less machines, not because we lack energy, because we have less people to operate them, and therefore we have less production. Very simple. Here you have something which is very logical, given what I've just said. Now I ask you a question. If we need to consume much less energy in order to fight climate change, do you think that we'll have a growing GDP? Do you think that it's going to be done in the blink of an eye? And because all this energy is fossil, we also have this curve, which is a logical consequence of what I've just explained before, which is that you also have roughly a straight line between the size of the GDP and CO2 emissions. So the only thing that works for sure, regarding addressing climate change is decreasing the size of the GDP. That's the only thing that works for sure. Maybe we can change for nuclear energy, renewables. Okay, we'll discuss that later on. But that's a bet. We are not sure that it will work. The thing that we are sure will work is decreasing the size of the GDP. So the story of the 19th and 20th century is very simple to draw. We have fossil fuels. As all natural resources, their apparition on Earth is free. I insist, their apparition on Earth is free. Oil is as free as air regarding the fact that it exists on Earth. Fossil fuels, they burn. So that allows to put machines in motion, and machines have transformed all the other resources that we have on Earth in order to build all the devices that surround us today, more than 100 millions of devices, various devices that we have done. This has enabled to change not only what we consume, but also the way that we are organized, because since machines work for us, we can devote our time to doing something else than growing potatoes or carving wood. What have we affected our time to? To working later, that's long studies, not working sooner, that's retirement, not working at all for part of the year, that's holidays, not working at all for part of the week, that's weekends, not working at all for part of the day, that's shorter days of work. So all these evolutions are the result of a growing energy supply. Jobs have moved from agriculture, where we have replaced farmers by tractors, fertilizers, that is machines to manufacture fertilizers, and trucks. And so people can work in industries than offices. Those are located in cities. So more energy, more cities, because we can change the way people are organized. Of course, more energy, we can move everywhere. Globalization. Globalization is the result of abundant oil. Before abundant oil, there were no globalization. Because it's so easy to get a car with abundant energy, we have built sprawling cities and not concentrated, etc. So when you look at the way countries have evolved, there is one reason why they have evolved about the same way everywhere, irrespectively of the political system in place, because they all had access to abundant energy. So the main driver of what happened over the course of the last 2 centuries is the conjunction of a stable climate, part 1, and abundant energy, part 2. Both these elements, of course, can have bottlenecks. We can have an upstream bottleneck because the energy supply is going to decrease even if we don't want it, because it takes 5 to 500 million years to manufacture this for the planet. And we use it at a rate which is absolutely not the same. We use it roughly 1 million times faster than the creation time of these resources, because it's created all the time, but 1 million times slower. So we will have a bottleneck upstream, and actually this bottleneck has already begun in some parts of the world. And we also have a bottleneck downstream, which is the fact that climate change has the ability, as I just explained before, to hinder our activities and prevent the system to go on. And in between, we have decided that the only thing that we will count to evaluate whether we are in good shape or not is the economic counterpart of the transformation of resources that are free into something else that is not free. It's the only thing that we count, and we consider that counting this is enough to count all this. Of course, it's an illusion. Counting only this, we can't see this coming, we can't see this coming. And as you probably know this famous joke, before the day he died, he was alive. It's going to be exactly the same for the consequences of this and this. They are going to happen with I would say, a short time to see them coming. Okay, so we are not going to have much time to prepare because counting this doesn't allow to see this and this coming from far. Regarding the upstream bottleneck, so I've elaborated a lot on the downstream one. This report, not sure that many people that are watching right now have looked at it or have even been aware of it, has been issued by the International Energy Agency 3 years ago. And they said, see, it's written very explicitly, that when you look at oil production and you take conventional oil production is all oil production on Earth, except shale oil and tar sands in Canada. So shale oil in the US and tar sands. So it's a big part, the shale oil and tar sands, but the rest is much bigger. So what it says is that, so that conventional production peaked in 2008, and since it has declined, even though the investments made by the oil companies since 2008 have been multiplied by 6. Okay, the annual investments have been multiplied by 6, even though, just because there is not enough oil remaining in the ground. The peak of oil discoveries, not oil production, but the peak of oil discoveries regarding conventional oil was the year I was born. And you can see I have a little gray hair. So it's not something that happened yesterday. It is something which is already very old, 60 years ago, in rough figures. This is something which is the consequence of the depletion of oil fields, okay? And it's going to increase. Conventional oil production is going to decrease more in the decades to come. And this is an investigation or a study that we have done at the SHIP project. We have hired, the former head of exploration for Total, which is one of the majors that we have in the world. We have hired the former head of oil field appraisal of Total. And we have hired the former oil expert of the International Energy Agency, who happens to be French for part of the time. And we have asked them to review the detailed data that can be found in a database which is published by Rystad Energy, written here, which is one of the 3 economic intelligence companies, so scouting companies in the oil sector. And so these people have a very detailed database of all the oil fields and gas fields in the world. And so the 3 people that I've mentioned have reviewed this data. And from this data, they have derived a perspective of the future oil production of the top 16 suppliers of Europe, top suppliers of Europe, which happen to be the 16 top producers in the world, except from Canada and Brazil. Okay. And the result of their analysis is the following. Post-COVID oil production is unlikely to go back to the pre-COVID oil production, which was here. Oil shale production is unlikely to go back to, unlikely to go back for long, I would say, to the pre-COVID shale oil production. And oil production is going to be roughly divided by 2 in the course of 30 years. So it's not a division by 3 that would be required in order to address climate change issues, but still it is fast, a division by 2. And because of what I just mentioned before, regarding the link between energy, that is the active fleet of machines, and GDP, it means that we will have to address, that's where I wanted to end, we will have to address a growing climate change issue with decreasing means. So there will not be green growth. That is not going to happen. We will have growing problems with decreasing means. And the longer we wait to address the issue, the harder we will be hit. Here you have a graph which just compares the change, the year-on-year change of oil production. It's oil consumption, but actually oil production is the same. And the year-on-year change of the GDP per capita. And what you can see is that both are very well adjusted. Actually, the GDP per capita is following with a small lag the change on the oil production. And it's a change on the oil production, not the oil price. I don't care about the price. This I'm going to skip because I'm running out of time. I will end with this. So this is a document that has been issued by the European Environment Agency a couple of months ago. The European Environment Agency is an official institution of the European Union, just like the Commission or the European Court of Justice. It's not an NGO. And as you can see, it says that it is unlikely that a long-lasting absolute decoupling of economic growth from environmental pressures and impacts can be achieved at the global scale. So you can have decoupling in some places. Denmark can decouple, okay? You can have a decoupling for a couple years or decades, okay? But you cannot have it at the global scale for Earth, and you cannot have it for long, okay? And you very well know that when an official institution writes unlikely, it means actually, I don't believe in it a single second. That's what it really means, okay? So again, that's the end of the story. It happens that the end of the story has been known for a very long time, 50 years. Some of you, if some people that listen are as old as me, you might remember the works of the Meadows team, Donella and Dennis Meadows at the MIT in the late 60s, early 70s. That led to this book called The Limits to Growth and to this Club of Rome that you might have heard of. These people at the time designed a model in order to understand what would happen to humanity wanting to achieve perpetual growth in a closed system, or in a finite system, to be more precise. So the finite system is Earth, which is modeled here with resources. You begin with plenty of resources, and of course they deplete over time. A population, which is not very high, food, which is not produced in high quantities, industrial production, not very high, and pollution, which is very low. And all this experiment begins in 1900. So they designed a model that says how the system is going to behave over time with people wanting to achieve growth. So what they say is that between 1900 and 1972, date at which the report was issued, sorry, it's date of report, I didn't translate it from French, all my apologize. Everything is growing regarding population, food, industrial production, pollution is not too much of a concern, and resource depletion is not too much of a concern. At the time of the report, they did not at all foresee or forecast that the collapse would happen soon. And actually, that absolutely didn't foresee that today the collapse would have already happened. Okay, so today they said, okay, if we want to achieve growth, we will still have growth. Resources will have depleted, but there will still be plenty. Pollution will grow, but still it will not be totally unmanageable, etc. What is interesting is what they said for after. What they say for after is at some time during the 21st century, the system collapses. The system collapses because not enough resources, too much pollution, not enough food, etc. And as you can see on this simulation, at the end of the 21st century, we are not 10 or 11 billion on Earth. We have come back to the population of the early 20th century. Because you cannot have perpetual growth in a finite system. That doesn't exist. Only in the mind of economists and political leaders that want to say any nonsense they can think of in order to be re-elected. But only in their minds, or only in their mouths, to be more precise. But in the real world, it doesn't happen. Nothing grows forever. My size doesn't grow forever. My physical possibilities don't grow forever. The wealth of someone doesn't grow forever. Nothing grows forever. Nothing. So if we don't pay attention to what is happening today, which is what we are doing, we don't pay attention, business as usual is this. This is business as usual, okay? It's not at all Alice in Wonderland that you can see in ever-growing scenarios where that doesn't exist. This is business as usual. In the climate models, the economy is not coupled with the consequences of climate change, and it is not coupled with resource depletion. It is an emission scenario. It is a scenario. It is not something which is realistic. It is a scenario. And I'm done. I hope it has not been too long. And now, if there are any questions, I will try at least to answer them with pleasure.
Many thanks, Jean-Marc. Do you hear me?
Yes.
Yes. Good. All right. I'm going to give you a few questions, given the limited time we have. I'm going to couple actually two questions together. And I'll ask them at the same time because I think they're somewhat related. The first question I got, which is in French, so I'm translating somewhat. It's someone apparently that thinks also that it's very hard to get rid of nuclear energy as a stable source of electricity, and that person is convinced that the countries that have nuclear should keep it, and those who don't have it should try to build more nuclear capacity. However, he notes that the majority of green parties everywhere, and he mentions the French in particular, are very hostile to nuclear. And the question that comes from that person is there any scientific argument in terms of fighting climate change that would be convincing on the side of those people against nuclear energy? And the other question that's related to that, and that one I can read literally because it's in English. Do you think we can, in the coming decade, substitute our current reliance on fossil fuels with a comparable volume of renewables?
I'm going to answer the second one first because it's shorter. So the short answer is no. I've already said it before. And the longer answer is the following. Today, when you look at renewable energies, the one that comes first is biomass. But actually, biomass needs space because you need space to grow trees or grow or grow anything that you are going to turn into energy. So biomass production competes with energy production from biomass competes with food production, competes with biodiversity conservation, because you need, if you say that you are going to leave in peace the ecosystems for biodiversity conservation, of course, then you cannot chop down trees to burn them. It competes with human infrastructure because you need the soil for human infrastructure. And so when you look at the available space in order to turn biomass into energy, you end up with figures that are not of the magnitude of what we use today. I'm going to take a very precise, very simple example. If we turned all the all the cereals that we grow today on Earth, about 2 billion tons per year, if we turn them into biofuels, it would give us about 1/4 of the oil that we consume today. Okay. And of course, we are not going, the Americans already do this very stupid thing that consists in burning 40% of the corn they grow to feed their big cars. Would be much simpler to have smaller cars and not grow corn to burn it. But that takes us back to what I've just mentioned before, which is that energy is a hard drug, and getting rid or accepting to get rid of part of what we have is something which is very difficult, even though it kills us. It's very difficult. Same thing for the excess of food. It's very difficult. So much for biomass. The second energy that we use in the world, the renewable one, is hydroelectricity. In order to have hydroelectricity, you need mountains. So if you are in Canada, huge country with small population, if you had in Norway, huge country compared to its small population, 4.5 million people, very small population, you can dream of living an industrial life with only renewable electricity, no problem, okay? But if you are in Belgium, flat country, as Saint-Brel, with 11 million people, you can just forget it. I mean, you have no mountains, you have one big river, so much for hydroelectricity, forget it. Then you have wind and solar. Wind requires huge device to collect energy because the energy which is contained into the kinetic energy of air moving around is very low. It is very low. In 1,000 cubic meters of air, so you take a room which is 10 meters in each dimension, 10 meters wide, 10 meters long, 10 meters high, okay? Say a shopping mall, small shopping mall. And you put all that air in motion, it's going to at 80 kilometers per hour, which is roughly 45 miles per hour. Well, all that air in motion going through a windmill will produce as much energy as what you have into 3 milliliters of oil, which is that much oil. So wind is not dense at all, which explains why you should build tremendous amounts of windmills in order to collect the energy coming from wind. Now, the day we have only renewable energy, how do you operate the iron ore mine? Today, you have huge trucks and huge cranes. Are you going to power them with electricity coming from windmills only? How do you power the boats that are necessary for iron ore to come to Europe, for example, where you have no iron ore mine? Yes, you have some in Sweden, a little. But otherwise, all the steel that we use in Europe, for example, we need the iron ore coming from elsewhere. Are you going to propel boats only with wind? And you cannot store batteries on boats that are big enough in order to action the boat. I mean, from Australia or Brazil, you just cannot do that. How are you going to perform all the chemistry which is necessary to manufacture all the parts that are made of plastic in the windmill the day you have only renewable energy? Okay, because you don't have oil anymore, and it happens that all plastics and all petrochemicals come from oil, etc., etc. So the idea that we can have renewable energy coming from wind and solar, which is highly performing in a world without fossil fuels, is actually an illusion. In a world without fossil fuels, you will have the windmills that I show on my picture before, that were the windmills before fossil fuels, made of linen, cotton, wood, and stone. Not very efficient. So today, renewable energies are cheap because they are kids of globalization, which is allowed by fossil fuels. The day we don't have globalization anymore, the price of renewable energies will soar. Wind and solar. It's obvious. I can predict it. So if we wanted in France to replace our energy consumption by only wind, we should have one windmill every kilometer in each dimension of the country, over all the country, every kilometer. Do you think it's possible? So the idea that we will be able to replace the energies that are dense, that are dispatchable, that can be easily stored and transported. Oil is the best energy that you can dream of because it is so easy to store and transport with a very small loss of the energy that we transport. This is why we have come out of the renewable world in order to go into the fossil world when we wanted an industrial civilization. So that's for renewables. So the answer is, if I care for the life of my kids, not a single second, I will bet that we can keep the civilization that we have today with only renewables. Now comes nuclear. Nuclear, in physical terms, is the only dense and dispatchable energy that we have. The only one that we have which is reasonably dense and dispatchable is hydroelectricity, but as I just explained before, this is not something that you can operate everywhere. Nuclear is dense. You have as much energy in the fission of 1 gram of uranium. You have as much energy in the fission of 1 gram of uranium as you have in burning 1 ton of oil. 1 milligram of uranium, 1 ton of oil. So it is a very dense energy, much denser than fossil fuels, actually, which is why it is interesting, because as it is very compact, it uses very small amounts of matter, therefore produces very small amounts of waste, even though this waste is something that we should handle with care, but it's very small amounts. And it uses very small amounts of space. The ratio of the space needed between solar and nuclear is 1,000 to 1. We need 1,000 less space to produce the same amount of electricity with nuclear than with solar. Very compact. It has a number of inconveniences. It takes at least 5 years to build a plant, if not 7, if not 15, as in France recently. You need highly qualified people to design, build, and operate the system. So you need to maintain the skills. You need to have them in the first place and to maintain them afterwards, which is one difficulty. The second difficulty that you have is that it is not an open market system, because when you have a device which is going to last for 60 years, if not 80, and that you take 5 to 10 years to build and 10 years to dismantle, there is no private company that can invest with reasonable interest rates in this context. So if a private company invests at its own risk in this context, it's going to require capital at 10% or more. And then you have astonishingly high prices for the electricity produced. So it is an energy which has to be managed by a state-owned company or has to be managed by the state itself. And it's no wonder if today the 2 leading countries regarding nuclear on Earth are 2, I would say, authoritarian countries, that is China and Russia. The most advanced countries today on nuclear energy are China and Russia. France is still advanced, but it is declining because there is no constant will regarding calling on nuclear energy. So it's one day yes, one day no, depending on what the parties think that the voters want to hear, which is in itself stupid, because actually, basically, the voters don't care. If you ask them whether they favor or not nuclear, okay, they will give you an answer. But if you ask them what is the most important problem in your daily life, spontaneously, nuclear will come very, 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 very low after traffic lights, crime, insecurity, finding a job, cigarettes, and whatever. I mean, basically, people don't care. But some people in the political world believe that it's something important to say in order to get people to vote for you. I don't have any silver bullet other than trying to educate the population in order to fight against this. It's hopeless to believe that these people will become reasonable by themselves. It's not the way a democracy operates. The Americans that have had Trump know it. So a democracy can put the power in the hands of people that are totally stupid or totally incompetent or totally ignorant. It's absolutely no problem. The best way to prevent that is to educate the population. So it's what I'm trying to do, but there is no other way. Regarding the question that was asked, is there a way so that the Greens stop saying that it's a good idea to pull out from nuclear? The answer is educate the population so that at the end of the day, people don't believe, even in the Green parties, that it's a good idea to say that we should pull out from nuclear to get more votes. And if you look carefully at what has happened in Europe recently, you will see advanced signs, early signs of this evolution. In Finland, the Greens have said that nuclear energy was green. In UK, where you don't have Greens, they say that nuclear energy is green. In France, we have right now an election to design the candidate of the Greens, so primary election. And there was a candidate, Delphine Bateau, that explicitly said that pulling out from nuclear was not a priority. She explicitly said that. So times are changing a little, and the reason why is because at the bottom, regarding educating the population, there is a growing number of people like me who just try patiently to explain what is nuclear and what it is not, the risks that it bears and the risks that it doesn't bear, etc. There is no other way. It's a slow way, which is the major inconvenience, but I have no other solution.
I'll follow up with another question that I'll read naturally that goes back to the point about valuation of natural resources that are free because they're given by Mother Nature. I read the question, in order to value our natural resources, is the solution to implement natural capital accounting? Could this lead to an economic crisis?
If we decided to account for natural resources in the accounting?
Yeah, is the solution to implement natural capital accounting? I don't know if that refers to a carbon account. No, it's broader than, it's natural capital accounting that's referred to, not carbon accounting. In order to value our natural resources, is the solution...
I see the question. Well, the carbon tax is an attempt of doing so. The carbon tax is an attempt of evaluating the fact that you pour a ton of carbon into the atmosphere. Could it lead to a recession? Yes, of course, because basically slowing down CO2 emissions is slowing down energy consumption. It is slowing down the active fleet. Well, so it's decreasing the active fleet of machines. Yes, but as I've explained before, we are going to get a recession anyway. What I've just explained with my last slide is that at some point, the natural state of the evolution is going to be a structural contraction and not a structural growth. And the question now is, should we manage it? or should we wait as long as we can and just suffer from it?
Thank you. A question about the level at which there's the expression carbon neutrality that's used very often. At what level do you measure that? Is that company level? Is that region level? Is that country level? Is that on a worldwide level? What is the relevant measure at which one can say that something is carbon neutral? Could it be a product, for instance?
The only, I would say, physical neutrality is achieved at the scale of the planet. It's the day emissions are balanced by sinks. So today we are overshooting. Emissions are over absorptions by sinks. And we have to go back to that state where emissions equal sinks. That's carbon neutrality. And actually we should, for the 1.5 scenario, we should even later on pump CO2 from the atmosphere while not emitting nothing at all. Not going to be very easy. When you scale down to a state or a company, you discuss of things that are very different. Regarding a state, you still own sinks within a state. So the idea that, for example, at the scale of US or China or France, you have both sources and sinks, forests, and or agricultural soils that you can manage in a different way. They can also turn into sinks for a while, for a very long time, for a while. And so in this state, at this scale, you can say that you have a kind of neutrality. But this neutrality says nothing on the dependency on fossil fuels. So it's not because you have achieved neutrality with sinks that you have that you're correctly covered against the risk of lacking fossil fuels, which is a risk in itself. Okay. When you go down to a company, what is called neutrality is because you balance the emissions that you believe you should count. I will elaborate on that, with some sinks, on some credits to be more precise, that you buy in order to trigger something somewhere that you count with negative figures. But this way of proceeding has plenty of loopholes. The first one is that when you buy a credit, you bring an additional financing to a project, but you don't bring all the financing to the project, since you are credited for all the savings of the project. So that's a first loophole. So if the credits bring 1 to a project that costs 10, it is the one that you bring that gets the whole benefit in your accounting of all the emission savings. Whereas I consider that you should get not 1, but a 10th of the. Second thing is that in the credits that you can buy, you have both projects that sequestrate carbon, trees, for example, and projects that are just aim at emitting less. But emitting less is not taking back your emissions. It is just emitting less. Third thing is that a lot of companies take into account only the direct emissions when they do this. But they depend on plenty of indirect emissions, upstream and downstream their value chain, which are also necessary and on which they also depend. So I mean, for example, if you sell cars and people are forbidden to emit through using their cars, you're out of business. You don't sell cars anymore. So, the boundaries are generally too restricted when you do this. The fourth loophole is that it says nothing on the fact that there could be a constraint on the fossil fuel supply. Same thing, you sell cars. At some point, there is not enough oil in the country in which you sell cars. You sell less cars. And the fact that you have bought credits doesn't prevent you from running that risk. Last thing, which is probably the most annoying for me, the day a company says it's neutral, it means that all the people that work within the company stop to think about how things could be done differently. Because if you are neutral, the problem is solved. So why on earth do you want to operate differently? You don't. So you just do nothing. You do nothing, and therefore nothing cares about the fact that one day or another you will have constraints anyway, but you have not thought about it, and so you will be hit harder. So claiming neutrality for a company is, in my view, a very, very bad idea. It is something that you should absolutely not do.
Thank you, Jean-Marc. I'm going to allow one last question because I see we're already over time, and I know people have commitments. And there are lots of interesting questions. And by the way, I'll put when I'll make available the recording of this this webinar for those who signed up, and also make available a link to the European Environment Agency report that was published a couple of months ago, and that is somewhat contradictory with what the official positions of the European Commission at the same time have been. I make a link available to that report to those who have signed up, and a few other items which I found very useful in terms of understanding what decoupling, relative or absolute means, because we get a lot of comments on this. So I'm going to allow a last, and I see my friend Thomas Lehmann has actually made the link available already on the chat. and I'm going to allow one last question, actually, to have a note of optimism. And actually, because people obviously, some people I see are getting a bit desperate, although one person says, "Thank you for a fantastic conference," I'm quoting, but do you have any good news for us tonight? I'll start answering partly this question. I personally have followed the work of the Shift project and Carbon 4, which I mentioned as the think tank, and the consultancies in which Jean-Marc, along with many engineers and actually many bright young engineers who've joined actually over the last 2 years. I saw the size of your company has increased tremendously over the last couple of years with top graduates from top engineering schools, and we see people working on solutions in a very difficult environment, and obviously saying to people that it's going to be easy is not a way to solve the problem. So you should say to the people that the reality is harsh, it's difficult, but then there's always things to do. And I know the Shift project and Carbon 4, along with many of your colleagues, are working on that. And on the website of your companies, there's a lot of interesting items and studies on this that I recommend to everyone. There's some items are even in English as well, so they would be available to everyone to make their own education. But is there any good news apart from that?
Yes,
that you can give us for us?
It's time to eat. No, the good news come always later on. I mean, the day that you learn something bad, generally that day, the only good news is that life continues. I mean, the good news is that we are not, I would say, totally incapable of doing anything. We are able to do something, but it's not going to be something done, I would say, at no price or at no effort. So the good news is that it is a challenge, and sometimes we like challenges. And the good news is that when we face collectively something that we should overcome collectively, what we gain is precisely sometimes more interaction, more social interactions. So on that side, it might be something interesting, I would say, because it is going to bring more sense. We will know more why we do things, will be more meaningful for us. But obviously, there is a lot of work awaiting us in order to both design what can be done, implement it, convince other people that there is a huge debate which is not as simple as it seems, and that we should collectively probably do things a little differently or very differently, and that overall it will be a better world if we do so. But I'm sorry to say that there is no miracle to expect. So that's another bad news, or not, I don't know. And the last good news, is that now you know, which is good news in a way.
Thank you, Jean-Marc, and I'm very sorry that we're going to have to wrap this up, because there's many questions that are going to be left unanswered. But I hope certainly for many people, we'll make the effort to educate ourselves, whatever profession we're active in, and this is a material also in the field of arbitration, where we're very much involved in energy disputes and climate change disputes. So I'm going to wrap this up. So those who are attending part 2 of this 2-part conference, we'll be seeing you tomorrow at 4:30 p.m. French time, Paris time. To those of you who've not yet signed up, if you still have time, because we will have jobs to do as well, you can still sign up on the website of the Paris Arbitration Week for part 2 tomorrow. Otherwise, I'll just wish all of you good evening, good night, good morning, or good afternoon, depending on wherever you may be located at the moment. Thank you all. Bye-bye.
Bye-bye.